What happens to your shoulder blades right now? They're flat, useless slabs of bone doing nothing but anchoring a few small muscles. But somewhere in an alternate version of human evolution, those same bones could have become something else entirely. A joint, an attachment point, the base of a wing. Most people imagine this as fantasy, but the physics, the biology, and the anatomy of what it would actually take are far stranger and far more brutal than anything in a fairy tale. Let's start with the math, because the math kills the dream almost immediately. In 2010, biomechanist Katsufumi Sato and a team of researchers studied the relationship between body mass and flight capability across hundreds of bird and mammal species. The pattern was consistent. As body mass increases, the wing area required to stay airborne increases even faster. This is called the square-cube problem. Wing lift scales with surface area, which grows by the square, but body weight scales with volume, which grows by the cube. A pigeon weighs about 300 grams and manages fine. A human weighs 70,000 grams. To generate enough lift, a flying human would need a wingspan of roughly 6 to 7 meters, wider than a small aircraft. But wingspan is only the beginning of the problem. Birds aren't just humans with wings attached. Their entire skeleton is redesigned for flight. Their bones are hollow, reinforced with internal struts like microscopic scaffolding. A bird's skeleton makes up as little as 5% of its total body weight. A human skeleton makes up nearly 15%. For a human to fly, roughly 2/3 of that skeletal mass would need to vanish. Every bone hollowed, every joint restructured. And that's before we even talk about muscle. Here's where the numbers get almost absurd. A pigeon's flight muscles, the pectorals that power each wing beat, make up about 20% of its total body weight. For comparison, in humans, our chest muscles make up roughly 1%.
To fly, a 70-kilogram human would need flight muscles weighing around 14 kilograms, attached to a keel-shaped breastbone that doesn't exist in human anatomy at all. Birds have this structure. It's called the sternal keel, and it's where those massive flight muscles anchor. Humans have a flat sternum, built for nothing more demanding than holding your ribcage together. So a winged human wouldn't just need wings. They need a completely different chest, a different skeleton, a different metabolism, and that last part might be the most punishing requirement of all. In 2007, physiologist Bret Tobalske calculated the energy cost of flight across different animal groups. Flying, it turns out, is one of the most metabolically expensive activities in the animal kingdom. Hummingbirds, relative to their size, burn energy faster than almost any other creature alive. They have to eat roughly half their body weight in nectar every single day just to survive.
If a human-sized animal tried to sustain powered flight, the caloric demand would be staggering. Some estimates put it at over 10,000 calories a day just to stay airborne for a few hours. That's 5 times what an average adult eats now. Which means winged humans wouldn't just look different, they'd live differently. Eating wouldn't be a social activity or a pleasure, it would be a full-time occupation. Entire economies would reorganize around food production because a flying population would need to consume at a scale no agricultural system in human history was ever built for. But say we get past all of that. Say evolution or some strange divergence millions of years ago solved the mass problem, the skeleton problem, the muscle problem, the metabolic problem. What would society actually look like?
This is where it gets interesting, because history already gives us a clue. Anthropologists studying the few human populations who've adapted to extreme physical demands, high-altitude Andean and Himalayan populations, for example, have found that these environments don't just change bodies, they reshape entire cultures. Diet, architecture, social hierarchy, even religious belief systems adapt around the physical reality of the environment. A winged species would likely develop vertical societies, cities built upward instead of outward. Status might be tied not to wealth in the way we understand it, but to wingspan, to flight endurance, to altitude access. The ground, the place every human civilization has been built on, might become the domain of the poor, the injured, the flightless.
And there's a darker layer to this too. Flight requires enormous individual energy investment, which means winged societies would almost certainly have far fewer offspring than ground-based ones. Every added gram of body weight makes flight harder, so evolution would likely favor smaller, lighter bodies. Shorter lifespans invested more heavily in fewer young, similar to what we see in many bird species today. In other words, a winged humanity might not have built cathedrals or written symphonies. It might have spent every available calorie simply staying in the air. So when you imagine wings, you're probably imagining freedom, soaring above traffic, above borders, above gravity itself.
But the biology tells a different story. Wings wouldn't have made us free. They would have made us hungrier, more fragile, and infinitely more dependent on a world built to feed a body that never stops burning. We didn't evolve wings. We evolved something else instead. Big brains, free hands, the ability to build machines that fly for us without any of the biological cost. Maybe that wasn't a consolation prize. Maybe it was the better deal all along.